In this video tutorial, we will look at the equilibrium constant, KEQ. At chemical equilibrium, a constant ratio exists between the concentration of the reactants and the concentration of the products. This is referred to as the law of chemical equilibrium or the law of mass action. Now, this ratio of equilibrium concentrations is known as the equilibrium constant, and we write it as KEQ. So EQ for equilibrium and K for the constant. Now, for the purpose of this course, we're going to consider KEQ to be a unitless value, as we are only interested in the magnitude of this ratio. Now, it's important to keep in mind that KEQ is only dependent on temperature. So when you change the temperature, you change this ratio, you change the KEQ value itself. If you want to learn why, I do have another video in this playlist that explains this concept. But moving ahead, let's take a look at this generic reaction. A plus B produces C and D. Notice the lowercase letters. Those lowercase letters represent coefficients from the balanced equation. So when you deal with the equilibrium constant, KEQ, you must always remember to balance your chemical equations, otherwise you'll be missing out on these pieces of information that are vital to the equilibrium expression. So if I were to write the equilibrium expression for this specific reaction, we would take the concentration of the products, so in this case the concentration of C measured in moles per liter, and the concentration of D measured in moles per liter, and raise them to their coefficients as exponents. So the coefficient for C is an exponent, the coefficient of D as an exponent. We then do the same in the denominator, except this time it's with the reactants. So we take the reactant concentration of A and the reactant concentration of B, measured in moles per liter again, but raise them to their individual exponents. In this case, the coefficient of A and the coefficients of B from the balanced equation. Punch this into your calculator, and that is your KEQ value, your equilibrium constant value for this specific reaction. Alright, so what's the purpose of KEQ? How do we use it? Well, let's pretend my KEQ value is 17. Well, I can also write that as 17 over 1. Since the product concentration is in the numerator and the reactant concentration is in the denominator, this tells me that at equilibrium, I'm going to have more products than reactants. So when KEQ is greater than 1, we say that the reaction is product favored. Conversely, if my denominator is greater than my numerator, then my reactant concentration at equilibrium will be greater than my product concentration. And we would say this is a reactant favored reaction when KEQ is less than 1. Now, if KEQ is a really big number, that tells me at equilibrium I have so many products and so few reactants, going in the reverse direction is very unlikely to occur. And we can say that the reaction is essentially irreversible from a practical standpoint. So as an example, gasoline, when burned in the presence of oxygen, produces carbon dioxide and water. But how often have you seen carbon dioxide and water recombining back into gasoline? It's not impossible, but it's extremely unlikely. And so a reaction like this would have a very, very, very high KEQ value, and we can assume that this reaction is one directional only, so you'd only draw a single-headed arrow, not the equilibrium arrow. As you can imagine, an extremely small KEQ value means that you have a huge reactant concentration in comparison to the product concentration, and so going forward is very unlikely to occur, and so the reaction is unlikely to proceed as written. So as far as you're concerned, this reaction will not proceed in the forward direction. So please don't blindly memorize these statements at the bottom over here. Instead, I want you to understand what they represent. If you have a KEQ value greater than 1, that tells you that the numerator is bigger than the denominator, and so you have more products than reactants. If KEQ is less than 1, that tells you your denominator is greater than your numerator, so there's more reactants than products. If KEQ is extremely large, then you have a lot more products than reactants, so much so that the reaction is practically irreversible. While an extremely small KEQ value shows that there is so much more reactants than products, as far as you're concerned, the forward reaction is unlikely to occur. So I want you to take a moment and try this question out. Looking at the KEQ values for each of these reactions, I want you to tell me, is it A, the reaction is practically irreversible, B, the reaction would not occur as written, or C, in this reaction, both reactants and products can be found at equilibrium. So give that a try, press pause, and then when you're ready, press play and we'll take it up. Alright, in our first example, we see an extremely large exponent. So the numerator is extremely large in comparison to the denominator, so I have a lot more products than reactants. So this KEQ is best described as being practically irreversible, which is A. In our next example, we have a negative exponent. That tells me that the denominator is significantly bigger than the numerator. So at equilibrium, we would have a lot more reactants than products. And so the best descriptor for this one would be B. The reaction would not occur as written. Over here, we have 1.6 times 10 to the power negative 3. Again, negative exponent, but not as big as this one over here. So although the denominator is bigger than the numerator, and we're going to have more reactants and products, there won't be a massive difference between the two. Instead, both reactants and products can be found at an equilibrium, which is option C. And again, in this case over here, we see a positive exponent, not a super large number, but it does show that we will have a greater numerator than denominator, and it will be product favored, but it is still reversible. So again, option C would be best to describe this scenario. All right, let's do a sample calculation. Calculate KEQ and describe the conditions of the system given that the following reaction occurs in a 2.5 liter rigid container. Now, there is a key word here in this question, and that is rigid container. And if you recall, a rigid container is one where the volume remains constant, so the volume will not change. So the first step is to write out our equilibrium expression. If you recall, KEQ is the concentration of the products divided by the concentration of the reactants. So I'm going to write the concentration of HI, which is the product, over the concentration of H2, which is a reactant, and I2, which is the other reactant. Don't forget that when we balance the equation, there is a 2 in front of the HI, and so the coefficient must be placed as an exponent for the HI concentration. From there, we can substitute our molar concentration values into the equation and solve for KEQ. Now, converting your mole values into a molar concentration is a common error that students will forget. So remember, these square brackets represent molar concentrations. And molar concentration, C, is equal to mole divided by the volume. So for the concentration of HI, I took 7.5 moles divided by the volume, 2.5 liters, and that gave me 3.0 moles per liter. I did the same for the other two reactants, taking their mole values divided by the liters, mole values divided by the volume, and that's where I got these values at the bottom. Alright, and since the KEQ value is a 50, I can assume that there's a 1 in the denominator, and thus the product is larger than the reactant, so this is a product-favored reaction. Alright, now the concentration of a pure solid or a pure liquid is constant, and it never changes. So long as they remain pure, their concentration, their density remains the same. So for instance, if I had pure water over here, and I took out, 10 milliliters, if I removed 10 milliliters of pure water, is this water now less pure? No, it's still 100% pure water. There's just a smaller volume of it, that's all. The same occurs if I add pure water to it. As long as I'm adding pure water to it, it still remains 100% pure. The density of the water remains the same. The concentration remains the same. Adding pure water to this doesn't make this more than 100% pure. It's still 100% pure. The concentration does not change. The same goes for pure solids, like let's take for instance chalk, calcium carbonate. Let's pretend this chalk is pure calcium carbonate. If I snap this chalk in half, would you now consider it to be 50% pure? No, it's still 100% pure chalk. It's just broken into smaller pieces, that's all. So changing the quantity of a pure substance does not affect its concentration, so long as it remains pure. Thus, the concentrations of pure solids and pure liquids, because they remain constant, because they don't change, they have no effect upon the equilibrium constant, or rather, they are already factored in to the equilibrium constant, and we can just omit them, we can just ignore them in our equilibrium expression. Let's take a look at this sample equation. A plus B makes C and D, where A is a pure solid and D is a pure liquid, but B and C are aqueous solutions. So I'm going to write out my equilibrium expression. So there's my constant is equal to products, C and D, over reactants, A and B. So products in the numerator, reactants in the denominator. If I rearrange this equation and place C and B together, while D and A are together, you'll notice over here, that's our equilibrium constant. And over here, this is also a constant because the concentration of D and A, they don't change. They are pure solids and pure liquids, they won't change. Well, if I bring this constant over to the other side, I now have a constant multiplied by another constant, and that is our equilibrium, KEQ value. So our KEQ value already factors in the concentration of the products and the reactants of pure liquids and pure solids. It's already built into the equation. We don't need to factor them in on the other side. we can just omit them and pretend they didn't exist. Meanwhile, the products and reactants that can change their concentrations do have to be factored into the equilibrium expression. So in this question over here, you're asked to calculate the KEQ value for this equation. Again, it's taking place in a 0.5 liter rigid container, so don't forget to convert your mole values into molar concentrations by dividing the mole value by the liters. Looking at the equation, I see that it's already balanced, so my exponents will all be 1s. But because the calcium carbonate and the calcium oxide are pure solids, we will omit them from the equation. They're already factored into the KQ value. Thus, the only concentration we need to worry about is that of CO2. I'll divide the 1.25 moles by the 0.5 liters to give me the concentration of CO2, resulting in a KQ value of 2.50. Again, because the numerator is bigger than the denominator, we say that this reaction is product favored. So the numerator is always the products, denominator is always the reactants. This is a product favored reaction at equilibrium. Alright, similar to KEQ is Kp, the partial pressure equilibrium constant. If you look at the equation for Kp, you'll notice that it looks almost identical to the equation for KEQ. They both describe the ratio of products over reactants, and they both have the coefficients acting as exponents. The only difference is that with KEQ, we were measuring the amount of products using molar concentrations, moles per liter, but with Kp, we're measuring the amount of products using pressure, or measured in kilopascals. So both KEQ and Kp tell the same story. If you have a big KEQ value or a big Kp value, that tells you that the numerator is bigger than the denominator. So you're going to have more products than reactants in both scenarios. So what purpose does Kp serve? Why would I want to use Kp over KEQ? It really depends on what's easier to measure. So with aqueous solutions, it's typically easier to measure their molar concentrations than to measure their partial pressures. Conversely, it's typically easier to measure the partial pressure of a gas than to measure its molar concentration. Alright, so both Kp and KEQ tell the same story. We just need to look at their magnitudes to determine whether the numerator or the denominator is bigger, and that will tell us if the reaction is product favored or reactant favored. Now, be aware the values for KEQ and Kp may not be identical, and in most cases they won't be identical. But so long as their magnitudes are similar, they both tell the same story. Now, sadly, our curriculum was nerfed and Kp is no longer a big component of it, so you are not expected to do any calculations involving Kp for this course. I don't think there are any questions in the textbook that involve Kp. But you are responsible for knowing what Kp is and what Kp represents. Alright, so to recap, KEQ is a value that describes the constant ratio between product concentration and reactant concentration once a chemical system has reached equilibrium. And of course, this ratio of products to reactants will not change unless the temperature changes as well. However, prior to equilibrium, this ratio is constantly changing. And during this time, the reaction quotient, QEQ, is used to describe the ratio between the product concentration and reactant concentration until we reach equilibrium. So essentially, QEQ describes the current ratio of products to reactants, while KEQ describes the ratio of products to reactants when the reaction's over, or when the reaction has reached equilibrium. So let's pretend we've got a chemical reaction where the KEQ value is 12. Because the numerator is greater than the denominator, that tells me that this reaction is product favored, so I should have more products than reactants at equilibrium. But what if this reaction is pretty slow? How will I know when I've reached equilibrium? Well, we take a sample of this, determine the concentration of the products, the concentration of the reactants, divide them, and we get QEQ. Now let's pretend our QEQ value is 5. Well, if I compare it to KEQ, which should be 12, I see that KEQ is greater than QEQ. So currently, I have more reactants than I should have, and less products than I should have. This tells me that I have not reached equilibrium yet, and that the reaction must move forward in order to create more products and shrink down my reactant concentration to what it should be. So that once I reach equilibrium, I'll have the correct ratio of products to reactants as opposed to what I have right now, which is smaller than what it should be. The same goes for scenarios where QEQ is greater than KEQ. So let's pretend I take a sample and I find that the product concentration is 30 when it should be 12, and the reactant concentration is 1. So in that case, I have a lot of products and very, very, very few reactants. So now, which direction should my equilibrium shift, forward or reverse, in order to reduce my product concentration while increasing my reactant concentration so that this very high ratio of products to reactants is reduced to the ratio that it should be at equilibrium? Well, I'm going to have to shift to the left. So once again, I don't want you to just blindly memorize these statements over here. Instead, I want you to understand what these numbers represent and to think of them in terms of numerator over denominator or products over reactants and which value is bigger. Alright, so once again, QEQ and KEQ, the exact same equation. The only difference is QEQ describes the ratio currently, while KEQ describes the ratio at equilibrium. And by comparing these two values, we can determine whether the reaction has reached equilibrium, or whether the reactant concentration is too high and so we're moving in the forward direction, or the product concentration is too high and we're moving in the reverse direction. Alright, so let's take a look at this example. What I want you to do is determine whether or not, based on these values over here, the reaction is at equilibrium, and if it's not at equilibrium, which direction must it shift in order to reach equilibrium. So there's the KQ value. You need to calculate QEQ and compare the two values together. So give this a try. Pause the video, press play when you're ready, and we will take it up together. Alright, so solving for QEQ, again, same equation as KEQ, products over reactants. Don't forget to put the coefficients as the exponents. So in this case, the equation has already been balanced for you, but on a test that may not be the case. You'll also notice that I've given you the molar concentrations. I've already divided by moles per liter. But again, that may not be the case on your test. But plugging these values into the QEQ expression, we see that QEQ is equal to 15. So right now the QEQ value is 15 over 1, while KEQ is 0.40 over 1. So at equilibrium, I should have more reactants than products, but right now I have more products than reactants. Since QEQ is greater than KEQ, that tells me I need to shift in the reverse direction to decrease my product concentration, while increasing my reactant concentration so I end up with the correct ratio of products to reactants. Alright, and that is our lesson on the reaction quotient, QEQ. This is just a simple example. In future videos, you will see how we can use QEQ to solve more complicated questions.